Hello, this is Matt Dean with A Plus College Ready, and today we're going to talk about rotary motion. Rotary motion is when a body rotates about an internal axis, like a wheel turning around an axle. In rotary motion, we look at things in terms of angles. Usually we measure it in radians instead of degrees. We don't use linear measurements. A radian, remember, is the angle at which if you take two radii of a circle and you orient them so that they intersect an arc that is equal in length to the radius. So this is equal in length to this, which is equal in length to that. If all three of those are equal, then this angle will be equal to 1 radian. 1 radian is equal to approximately 57.3 degrees. It's also it's also important to remember that 2 pi radians is equal to 1 revolution, which is equal to 360 degrees. There's some equations to be familiar with rotary motion. Delta x is linear displacement. If you want to know the linear displacement of something going in a circle, you're going to multiply the radius of the circle of rotation times the angular displacement. So this is the displacement in radians. If you multiply that by the radius, that's going to give you the displacement in terms of meters. Angular velocity, this is angular velocity. It's equal to the change in angular displacement times time, or divided by time rather. So that's going to give you an angular displacement in radians divided by time in seconds. For angular velocity, you'll get a quantity in radians per second. Also notice if you want the linear velocity, you're going to take the radius times the angular velocity. When you multiply those together, you'll get an answer in meters per second. Sometimes you'll hear that velocity called the tangential velocity. That's the linear velocity, the velocity in terms of meters per second. You can also measure an angular acceleration. So just like, remember that linear acceleration is equal to change in velocity over change in time. We could think of angular velocity as change in angular velocity over change in time. Gives us an angular acceleration. Angular acceleration should be measured in radians per second squared. If we need the linear equivalent to the angular velocity, we're simply going to take the radius times the angular velocity. If we multiply those together, we'll get a linear velocity in meters per second squared. So here are some other equivalents or comparisons between translational or linear motion in this column and angular motion in this one. So here they use S for displacement. We're usually going to use delta x. Delta x is equal to r times angular displacement. The linear velocity is r times the angular velocity. The linear acceleration is r times the angular acceleration. We've got time. We'll talk about force and torque in a minute. We know that net force causes acceleration in linear systems. Net torque causes angular acceleration in rotating systems. We know that linear momentum, P, is equal to mass times velocity. Well, angular momentum, L, is equal to the moment of inertia times the angular velocity. And also with kinetic energy in a linear system, kinetic energy is 1/2 mass times velocity squared. In a rotating system, kinetic energy is equal to 1/2 times the moment of inertia times the angular velocity squared. We also have rotational equivalents to our translational kinematic equations. So here we have displacement equals velocity times time. Here we have angular displacement equals angular velocity times time. Here we have final velocity equals initial velocity plus acceleration times time. Here we have final angular velocity equals initial angular velocity plus angular acceleration times time. Here we have displacement equals initial velocity times time plus 1/2 times acceleration times time squared. Here we have angular displacement equals initial angular velocity times time plus 1/2 times angular velocity times time squared. And then the final one, here we have the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. Here we have the final angular velocity squared equals the initial angular velocity squared plus 2 times the angular acceleration times the angular displacement. So there are rotational equivalents to the linear kinematic equations. And remember, at least the bottom 3 assume a constant acceleration. Another important idea in this unit is torque. Torque is a force-like quantity which causes an object to undergo angular acceleration. You want to think about torque in rotating systems like net force in linear systems. Torque can be calculated using the equation F force times R, which is called the lever arm distance, times the sine of theta, where theta is the angle between the force vector and the moment arm. So we can see in this picture up here that typically we would grab this wrench and we would pull down like this. So this is the moment arm, the distance from the center of rotation to the point at which the force is applied. Notice right now, with my drawing, the moment arm and the force are at a 90-degree angle to each other. So if we go back to this equation, in my picture, this is a 90-degree angle. The sine of 90 is 1. So we might, in that situation, just write T equals FR. So if the force is at a 90-degree angle to the moment arm, the sine of theta doesn't really matter because the sine of 90 is 1. But if that force is applied at a non-90-degree angle, like in this case, to calculate the torque, we would need to know the angle between the moment arm and the force, and we would have to plug that in as theta. So when you apply a force at a 90-degree angle to the imaginary line leading from the axis of rotation to the point where the force is applied, you obtain maximum torque. As that angle changes or decreases, the torque also decreases. It's important to know that torque is a vector. It's a vector quantity. Torques can cause counterclockwise rotation, and those that do that are called positive torques. They can also cause counterclockwise rotations, and those that do that are called negative torques. Again, torque is similar to force in rotational systems. If there's no net torque, objects don't undergo angular acceleration. Let's also talk about equilibrium for a minute. We've dealt with translational equilibrium several times in this course already. Translational equilibrium happens when the sum of all the external forces acting on an object is equal to 0. Since force is equal to mass times an acceleration, another way to look at this is that an object is in translational equilibrium when it's not accelerating, when it has 0 acceleration. This can mean either the object isn't moving at all, or it might be moving at a constant velocity. Rotational equilibrium occurs when the sum of the external torques acting on an object is equal to 0. In this case, the object will experience 0 angular acceleration and therefore will either not rotate or is rotating at a constant angular velocity. Static equilibrium occurs when the sum of the external forces acting on an object is 0 and the sum of the external torques acting on the object is also equal to 0. In this case, the object is in both translational and rotational equilibrium. Now let's go back to torque for a second. Here we have Newton's second law, F net equals ma. Now remember that A is equal to R times angular acceleration. So we substituted for A, R alpha in this case. All right. Also remember that torque can be equal to Fr. So here we took torque for force, we substituted torque for force. So since torque is equal to Fr, we had to multiply the right side of this equation by another R. So that gave us torque equals mr squared times angular acceleration. Mr squared represents an object's rotational inertia, which we indicate with the letter I. Think of rotational inertia in a rotating system like mass in a linear system. So if we do a little simplifying here, if we use I instead of mr squared, we come up with this equation. T equals I times alpha. Essentially, this equation is Newton's second law for rotating objects, that net torques equal to moment of inertias times angular acceleration. Or we could solve it out as angular acceleration is equal to net torque divided by moment of inertia. Remember, alpha is angular acceleration, I is the rotational inertia, and it's a property of a rotating system which depends on not just the mass, but also the distribution of that mass in the system. The larger I, the harder it is for an object to acquire an angular acceleration. Let's also talk about center of mass for a second. The center of mass is the point where all of the mass of an object is concentrated, or at least we can think of it that way. When an object is supported at its center of mass, there's no net torque acting on the body, and it will remain in static equilibrium. If the object is uniform, like say a meter stick, the center of mass will be at the exact geometric center of that object. If the shape is irregular, the mass will be closer to the heavier end where there's more mass. So there's lots of problems related to the center of mass and rotation, lots of example problems. Here's one that we'll see a lot on our rotation problems. All right, so let's look at this problem. So we have a seesaw. It consists of a pivot and a heavy uniform plank, which is 1.6 meters long. A 12 kilogram box is placed at one end of the plank. How far from the other end should the pivot be so that the plank is balanced? All right, so we take a 12 kilogram box and we put it on one side. Let's think of this as the center of mass, the point at which all the mass or weight of that box acts. If that's the only object there, the pivot point or the fulcrum has to be placed between the 12 kilogram box and the center of mass to balance out the plank. For it to be balanced, for it to be in rotational equilibrium, the torque on the left-hand side of that fulcrum has to be equal but opposite to the torque on the right-hand side. We know that torque equals F times lever arm distance. F times lever arm distance. So on the left-hand side of that fulcrum, the force is going to be the weight of the 12 kilogram object. So we're going to say 12 kilograms. We're going to multiply it by G. We'll use 10 for G to make it a force. And we're going to call this distance between the box and the pivot point, we'll just call it X. That's got to be equal but opposite to the torque on the other side. Well, the torque on the other side is caused by the weight of the board itself. So that's going to be the 24 kilogram board. Again, multiply by G so that it becomes a force. If the distance between the box and the fulcrum is X, then the distance between the fulcrum and the center of mass has to be 1.6 meters minus X. I'm sorry, 0.8 meters minus X. Because the whole board is 1.6 meters long. Since it's a uniform board, the distance from the center of mass to this end has to be half the length of the board, 0.8. So if the distance from the box to the fulcrum is X, the distance from the fulcrum to the center of mass has to be 0.8 minus X. All right, so if we do the algebra here and we solve for X, we end up with X equal to 0.533 meters. So that X is the distance between the 12 kilogram box and the fulcrum. That is not what this problem asks us to find. It asks us to find the distance between this end of the seesaw and that fulcrum. So if the distance from this end to the fulcrum is 0.533, then the distance from the fulcrum to this end has to be 1.6 minus 0.533, which comes up to be 1.067 meters. We only had 2 sig figs in this problem, so really 1.1 meters would be our answer to this particular problem. The key thing to think about in this problem is when you need something to be in rotational equilibrium, The torque on the left side of the fulcrum and the torque on the right have to be equal but opposite. Also, you need to think of the center of mass as the point at which all the mass or all the weight of the object is located. Now, we already mentioned the moment of inertia, but remember the moment of inertia, capital I, is a measure of an object's resistance to change in a rotational direction. The moment of inertia has the same relationship to angular acceleration as mass does to linear acceleration. More moment of inertia means it's harder to accelerate an object. The moment of inertia depends on the distribution of the mass in the body with respect to its axis of rotation. For a point mass, the moment of inertia is the mass times the square of the perpendicular distance to the rotation reference axis and can be expressed as I equals mr squared. Moments of inertia for objects of different shapes are included on the next slide. And typically you would need to be given these formulas. So you can see the moments of inertia for objects of many different shapes. For example, a solid sphere, moment of inertia is I equals 2/5 mr squared. Whereas for a cylinder, 1/2 mr squared. Let's also talk about angular momentum. We'll see angular momentum symbolized with capital L. Linear momentum, if we remember back to several units ago, is the product of an object's mass times its linear velocity. Momentum is also a vector. So in linear momentum, it's sometimes we'll use that as P. It's actually rho equals mv. Linear momentum is conserved in a closed system. It's kind of an indicator of how hard it is to stop a moving object. Angular momentum, on the other hand, can be thought of as the radius, or the r, times the linear momentum. That might give us mvr, since linear momentum is m times v. We can also think of angular momentum as the product of an object's moment of inertia and its angular velocity. And that's typically how we're going to calculate it in this class. So angular momentum equals I, the moment of inertia, times the angular velocity. Angular momentum describes how hard it is to stop a rotating object. Like linear momentum, it's conserved as long as no net torque acts on the object. Sometimes we need to determine the direction of angular velocity or the direction of angular momentum. And we're going to use the right-hand rule to do that. To use the right-hand rule, you're going to grasp the object that is rotating, and you're going to wrap your fingers in the direction of rotation. If your thumb on that right hand points up, that means that the angular velocity and the angular momentum are acting in the upward direction. On the other hand, if your thumb points down, that tells you the direction of the angular velocity and angular momentum are in the downward direction. So your thumb is going to tell you the direction of the angular velocity and the angular momentum as long as your fingers are wrapped in the direction of rotation. The direction of angular velocity and angular momentum are always perpendicular to the plane of rotation. As we said a minute ago, angular momentum is conserved when no external torques act on a system. This can be observed when watching like an ice skater that's spinning around in a circle. When the ice skater starts to spin, she generates a rotational velocity by applying a torque to her body. She has angular momentum. And that angular momentum is equal to the product of her moment of inertia times her rotational velocity, or angular velocity. To increase the velocity, she pulls her arms in. By pulling her arms in, some of her mass is moved closer to the rotation axis. This decreases her moment of inertia. When her moment of inertia decreases, her angular velocity must increase because angular momentum is conserved. So here's an example problem dealing with angular momentum. Angela spins on a rotating pedestal with an angular velocity of 8 radians per second. Bob throws her an exercise ball, which increases her moment of inertia from 2 to 2.5 kilograms times meter square. What is Angela's angular velocity after catching the exercise ball? Neglect any external torque from the ball. So remember, angular momentum is equal to I times angular velocity. So let's take the angular momentum, let's set the initial angular momentum equal to the final angular momentum. So her initial angular momentum would be her moment of inertia, 2, times her angular velocity of 8 radians per second. That's going to be equal to her final angular momentum, which is going to be her new moment of inertia, 2.5, times her new angular velocity. So let's solve that out for the angular velocity. So 2 times 8 divided by 2.5. So she's going to have a new angular velocity of 6.4 radians per second. So since the moment of inertia increased, the angular velocity decreased. Here's another sample problem. A disk with a moment of inertia of 1 kilogram times meters squared spins on an axle through its center of mass with an angular velocity of 10 radians per second. An identical disk, which is not rotating, is slid along the axis until it makes contact with the first disk. If the two disks stick together, what is their combined angular velocity? All right, so this problem is another example of conservation of angular momentum. To begin with, we just have one disk rotating. So its angular momentum is going to be equal to its moment of inertia times its angular velocity. So that's 1 kilogram times meters squared times its angular velocity of 10 radians per second. Then the second disk of identical mass and mass distribution is slid onto the same axle. They bump together and now they continue to spin. Well, that means that angular momentum is conserved. So that means that the initial momentum of the system has to equal the final angular momentum of the system. Sliding that other disk on, what that changes is the I. And it's going to be twice as much. So the new moment of inertia is going to be 2 kilogram meters squared. And that's going to give you a new angular velocity. Well, if we solve that out for angular velocity, we're going to get a new angular velocity of 5 radians per second. So by sliding on that extra mass, since angular momentum is conserved, there's extra moment of inertia. So the velocity has to decrease, and it decreases to 5 radians per second. One final thing we're going to talk about with rotation is rotational kinetic energy. We've talked about the linear version of kinetic energy before, the translational version, and that was equal to 1/2 mass times velocity squared. But rotating objects also have the ability to move other objects. We might think of kinetic energy as the ability of an object to move something. Rotating objects also have kinetic energy, and we can calculate that rotational kinetic energy using a translational analog. Essentially, rotational kinetic energy is equal to 1/2 times the moment of inertia times the angular velocity squared. If an object is undergoing both translational motion or linear motion and it's rotating at the same time, for example, maybe a tire rolling along a surface, it's going to have both forms of kinetic energy. It's going to have the linear or translational kinetic energy and the rotational kinetic energy. So we might see them in an equation where the total kinetic energy is equal to 1/2 mv squared plus 1/2 I times rotational velocity squared. So here's an example problem where that might be true. All right, so in this problem, we have a piece of string wound around the outer edge of a 5 kilogram cylinder of radius 2 meters. So think of it almost kind of like it's a yo-yo. And let's say that string is attached up here to a ceiling. The radius of this wheel is 2 meters. The cylinder is 4 meters above the ground. So here's the ground down here. The distance from the center of mass to the ground, vertical distance, 4 meters. So then we let this cylinder go. So as it goes, the string is going to unwind from the outer edge of the cylinder, and it's going to experience both translational motion and rotational motion. We're trying to find the velocity, so this is asking for the linear velocity of the center of mass as it reaches the ground. It's kind of intimidating looking problem at first, but this is a conservation of energy problem. When the object is up here, it has potential energy, gravitational potential energy, mgh. And as it falls, it's going to have both translational kinetic energy, 1/2 mv squared, and it's going to have rotational kinetic energy, 1/2 I times omega squared. Well, notice that the masses cancel out. Well, not yet. Let's go back and make another substitution before the masses will cancel out. The moment of inertia of a cylinder is 1/2 mr squared. So let's substitute that in here. So again, the masses are going to cancel. Mass is part of every term. So the mass here cancels. Mass over here cancels. So now we have GH is equal to 1/2 V squared plus 1/4 times r squared times omega squared. Now that still looks a little intimidating because we don't know either V or omega. But what we can substitute in is that we know that omega is equal to, think back to this, V equals R omega, which means omega equals V over R. So let's substitute V over R in there for omega. So the R squareds are going to cancel out. So essentially we're going to end up with GH is equal to 1/4 V squared plus 1/2 V squared plus 1/4 V squared. So that's 3/4 V squared. We solve that out for V. So V is going to be equal to the square root of 4/3 GH. If we plug in our numbers, we plug in G, 10, we plug in the height, 4, we end up with a velocity here of 7.23 meters per second. So this is a situation where an object is rolling without slipping, and in that case, we're setting its initial potential energy equal to its translational kinetic energy plus its rotational kinetic energy. And that's it for our presentation on rotation.